My name is Richard Freudenberger. I'm the Energy and Resources Coordinator here for the farm. So we have 3 different locations, 3 different facilities. We are a research farm. We have 3 farms and 4 greenhouses. The biochar facility makes a wood vinegar, which we're testing and finding new uses for the co-product of the biochar. And we package the biochar here into sacks and use it in the fields and on crops, and really just do a lot of active soil research and crop research and energy research. And in this workshop, we're going to take our next hour or so, hour and a half, and talk about the soldier fly facility that we've built. It's been sort of a long road, but we've made changes on the way. The class here is really about ventilation and climate control technology in the soldier fly building. It's about earth tubes, earth-coupled cooling, the use of solar energy in making that function. Basically, I'll go through 4 or 5 areas that we have to be aware of in planning a cooling tube project. And I will also spend some time in not being negative, but trying to make people aware of the fact that there are probably certain situations in which earth-coupled cooling tubes are not as effective as they could be. And at some point, there's a return on investment factor. In other words, you don't want to spend several $1,000s doing something if it's not going to get you much back. So that's something to think about before you embark on it. But in our case, we have a fairly small building. It's actually a shipping container. It houses our breeding facility for the soldier flies, which at the moment has been modified to make the earth tubes work. And then the earth tubes were buried in conjunction with some other landscaping we were doing. This building was built up against a bank, so we were limited in the space between the building and the bank. In your cases, if you're doing things, you probably won't have those restrictions. There are some other things to think about, but this is a physical limitation. We only had 18 feet of width, and then we had about 200 feet of length to work with. In most cases, that 200 feet is going to be far more than what you really need to have for a normal facility. The point of the class is not to duplicate what we did necessarily. We just want to give you enough parameters and insight and to be able to put it all together and look at it in your personal situation. If you have a flat spot, it probably doesn't even have to be flat, really. You have to have enough ground space to be able to take advantage of it, and soil and a few other things. So basically what I will be talking about is the building itself and what we did to the building. It could be this room, it could be the container I used, it could be anything you have back at the farm or home. And how many people here actually are in like a residential, like a non-farm situation where it's pretty much just a suburban type setting? Is everybody or nobody? One? Okay. And then everybody else is on like a small either farmstead or some small amount of acreage that you can actually work with something. Okay, so that's good. So we have the building. We'll talk about the tubes and what we need to do with the tubes. We'll talk about the solar chimney, the aspects of the solar chimney and what that does. We'll talk about the active fan controls that were put in place to back up the solar chimney. I think with the size of the class we have here, it's easier just for me to run through the images here. It shows each aspect of what we're doing. That'll familiarize you with what we did, and then we'll be able to go out back here and actually look at everything and go through all that there, and then we can come back in and I can actually talk about and take questions about what to think about when you're designing or buying, or what things going to cost, how much math is involved, that kind of thing. Materials, where you get some of the stuff, how important it is. Some things which would seem like they're really critically important actually aren't as much. And then some things which seem pretty much like a regular building science or construction thing are actually pretty important, so we want to make sure you know about that. The soldier fly is a small, non-invasive insect. It sort of looks like a wasp. And in fact, in the summer when I was cleaning up around the access opening, they will get out and they get all around, and I was in the midst of picking them off, and I realized once my finger got jabbed, this is not a soldier fly, this is a wasp. That's sort of what they look like, just a skinny black wasp. What they do is they produce a larvae, which is extremely beneficial to us in digesting anything that would normally compost and take time to compost. We will use the soldier fly in doing that at a much more rapid rate. So all that's done much more quickly, and then we can also use the composted material in various ways around the farm. We always need compost. Or we mix it in with other working compost, or we can mix it in with other soils. And we can also then feed the larvae to our livestock, our chickens. If we do have any issues, we'll analyze the situation. We can always make modifications. That unit there is, for all intents and purposes, is finished, but it's not ever really finished, because right now I want to put more soil on the roof, maybe make the access window bigger. There's a lot of things that we could be doing, but basically that thing needs to be shut up so that we don't have a rodent control population. I mean, if you leave everything open and leave the tubs of compost and food waste and whatever else out in the open, that, you know, you're just inviting vermin. We close the facility so it's totally vermin-proof, and then the insects can fly in and out the window, which has a screen on it that's big enough to let the bugs in and out. We would not leave it open for overnight or anything like that. It's just not a good practice. The building shipping container is 20 feet long and 8 feet wide, and these are the actual exit tubes from the underground subterranean circuit that we have. That's the solar chimney. These come in all along this end wall, precisely 18 feet away. There's the solar chimney, which is a hole we cut in the roof of this container, which is all steel. And the solar chimney sucks air up. When that building is closed up, the only place it can get fresh air to replenish the air that's been sucked up is through these tubes. So it's a wonderfully simple, elegant solution, which definitely is not an extremely cheap way of doing things, but over time, since there's very little energy involved, if any, well, there will be, because the fans will have to come on occasionally, but in general, it's over a long term. There's really nothing to wear out. The sun's always going to shine. The chimney's always going to work. I mean, the maintenance on this thing is very low. The whole thing should and will work the way it's intended to work. If you poke around a little bit, there's a lot of variations in design as to how big those tubes are, how long they're going to be, what material they are. You know, these are 6-inch tubes. Can they work at 4? Can they work at 12? I've seen them where they're actually 6 feet wide. People can actually walk through them like a sewer pipe. When you start getting up to even 12-inch pipe, you start to get into real money. So, you know, we really have to think about this before we get into it. And, you know, the idea here is to try to keep the cost down to an affordable point. And may have a farm-scale operation that, you know, might cost a little more than most people would spend, but at least the principles can apply to a smaller or less expensive use of those principles. There's a retaining wall behind there. We only had that much room between that building and that wall to work with. So that's about 15 working feet of thermal control going on, but I think it's 18 feet precisely from there to the building. Now he's about 5'10". The container itself is up here in the corner. We didn't place it yet. That's been set aside. The actual block wall, which you had in the picture before, was not there to begin with. So basically, while they were building the wall, we bid the whole project so that once the equipment gets out here, we could take care of the whole thing. So myself and our other staff guy, Mark Henderson, we shot this for levelness and, you know, figured out all the trenching and all that stuff, and they just commenced to digging. This is something to think about. I mean, normally 3 or 4 feet is about what you would consider safe. This soil is particularly stable, so we told each other we were not going to get in that hole unless we had some way to hold back the walls, but we never really had to use it because we had enough room there, and the soil was extremely stable. You know, we really weren't in there that much, and it was really basically we're able to pass the pipe sort of down in there and move it along, and didn't really have to spend a whole lot of time in the trench. The terrain changes, but the depth is 6 feet along the whole thing, except at the very end, and I'll show you why that is. But that was not as critical, but it sort of had to be. Important part here is to keep it consistently level. In other words, you don't want a lot of ups and downs, because if humid air is coming through that pipe, moisture is going to condense and eventually gather in the bottom of the pipe, and you have to be able to pull that out. We have never had to yet, and it's been there for a year. At some point, we probably will have to. You don't want a big hump, because once the water fills up and actually blocks the pipe, that's it. I mean, you can suck it out with a long tube and a vacuum, but you don't want to have any point at which it's going to gather more than, you know, a little bit. You want it to slope ever so slightly towards the building, towards the point of use. There has to be what we call standpipes, or some methodology of being able to get to the lowest point in the pipe to be able to put a shop vac or a suction pipe of some type down in that thing. It's going to be 6 feet down, and suck all the water which is gathering down in this, right in that region there. Just suck that out. Make it easy. If we did not have those pipes, it still could be done, but you'd have to snake a fairly stiff vacuum hose down that thing from this end, and, you know, get it and sort of twist it to, you know, it's just not that easy. So we just wouldn't didn't want to do that. So I put those standpipes in. Of course, everything's buried. They're actually under the surface of the soil by 6 inches, so we can drive over them. And I've marked them on a little map and wrote on the building wall, 37.5 inches, 87.5 inches, 117 inches on this line, so you know where to get them when you dig under there. If we didn't have all that stuff in there to fix this pipe, if there was a problem, you have to unearth the whole thing. That's a lot of dirt to move. It's expensive. This, by the way, is a high crush, 3,000 pound per square inch, which is like an incredible amount of pressure pipe. We don't even come near that at 6 feet. It's a very thin wall, but very strong, 10-foot lengths. They come in 10s and 20s. I've got the 10s because it's just easier to carry. That's what they had here. Each stick, which is 10 feet long, the last 6 inches is formed a little bit bigger so the skinny end can fit into the other end, and you can still cut the bell off and use a standard coupling if you have to, or if you want to. So it's a very traditional, common, fairly inexpensive pipe. The plastic material, for reasons which I'll explain, is probably ideal for what we're doing, just in the sense of the way it's made and the way it flows. At this end, the exit end, 192 feet from the entrance end, we have pipes. They're only down there probably 2.5 feet. To be able to meet the inlets we cut into the top of this container, had to go through a little bit of convolution to get to that point. In other words, they come in, they go up, make a right turn, make another right turn, and go up at a 45-degree angle, which is the easiest thing to work with. You don't want to have odd, you don't really want 22.5s or any other things. I mean, just hard to work with. On the other hand, you want to minimize the amount of right angle bends, just for airflow circumstances. So a right angle bend is almost twice as constrictive as a 45. It pretty much works along those lines. Straight is ideal, but you have to make a bend someplace. So fortunately, this pipe is slick enough that those bends aren't all that invasive in the overall design. So the building itself, no matter whether it's the container or whether it is an outbuilding or a building you start fresh, or if it's a small shop or whatever it might be, the building itself has to be insulated fairly well. You can't have gaping air leaks, not only because the heat loss would be too great, but also because the whole idea of the solar chimney and the suction of the air and the movement of air will not function passively without power, except for the sun. It will not function if there's big holes in the walls, because the air will be sucked in through those holes and less will be sucked in through the tubes. If the holes are big enough and they start approaching the size of the tube diameters, then it's not going to suck anything through the tubes unless you put a fan in it. So we carefully have gone through and we've insulated the entire inside of that chamber. This is basically, I wanted to show you another thing we did here. The cold air in the winter is underneath there too, so it's not good enough just to do the ceiling and the walls. It has to be the floor too. And since we have so much hot water available from our biochar facility, I mean, we're close to a million BTUs an hour. There are specific jobs that biochar facility, other than making biochar, has to do, and that is provide hot water for several different things here in the greenhouse and the drying room at the end, and this facility and some other things. So we put in this radiant floor heating system on top of the extruded polystyrene base, and this is standard construction procedure. Our biochar crew has experience in this. We had 4 inches of extruded polystyrene, which is water resistant, fairly high R value material. It is not standard blue board. It is XPS, or extruded polystyrene, which is an important distinction. Mainly the distinction is that it's denser, stronger, has a higher compressive strength, because we're going to have weight from the soldier fly bins and the concrete that goes on here for the floor. So the compressive strength, the ability to resist crushing, has to be there. So the XPS type of styrofoam has that ability. It's also water resistant or waterproof. So it does not mind being wet, and it still functions when it's wet. So in this case, it's not that important because we don't have water leaking in there. The fact is that humidity, condensation, that kind of thing does get in there. It does have to be resistant to that kind of stuff. So basically what we're doing is pumping hot water through the tubes. That, up to this point here, we put in, it's about a 4-inch floor, probably a little bit overkill, but it's a 4-inch floor of concrete. Was screeded in here after this was all pressure tested. the hot water runs through the tubes and warms the concrete, and the concrete oozes heat out into the facility. This is how we handled that. These are 2-inch, 4 feet by 8 feet by 2-inch thick R10 for each 2-inch sheet. 2 of them together, which is what we got, 1, 2, is R20, which is 1 R value over the R19 that most houses are built with. So that's, okay. You can go thicker. Just we didn't need to. The situation is also the thicker you make those inside walls, the more space you lose inside the building. We were already getting to the point where I was feeling a little bit like we're too tight. These are actually metal studs. They're standard commercial construction type things. You can get it even at Home Depot or any builder's supply that serves contractors. They're in the same dimensions as a regular wood stud, but they're galvanized sheet metal. They're pretty inexpensive. You can screw into them, and just like you would wood sheet metal screw. So we tack welded them into the spaces. You can see it's a ribbed container, so it goes boop, boop, and goes up and down and up and down. So we went into the recess, and we tack welded the studs in there. On the walls and the ceiling, we laid 2 sheets, 1 sheet, and then where the seams met, we covered that with a full sheet. So the seams never meet each other. They're always staggered, so there's no air leakage. And then big, long, I think there were 5.5-inch, they're special, like decking type and other use screws. They come in boxes like 36. They're skinny, strong, and they come in all different lengths, but we used like 5.5 or 5-inch long ones to get through the sheathing that we put on the inside wall and the 2 layers of XPS, and then they bore right into those sheet metal studs. We do not want to bore through the wall of the building because you don't want a rust spot at that point. You just want to go, that's why you have to figure your screw length, just enough into the galvanized stud to catch it. They have a sort of a special thread that really does catch it. So on the top, because we put soil on the roof, I had them put in tubular steel, which actually can support the weight. The containers are extremely strong on the corners and the walls, but they're not as strong on the roof. And although I'm pretty sure now with the thin roof, with the thin soil layer we put up there of only it's less than 6 inches, probably would have handled it, but we didn't want to take the risk. So we just, instead of using the thinner galvanized ones, we just used these heavier, I think they were 2x3 channel iron. I figured out where the pressure would be, and we stretched them across there. So there's 5 of those or 4 of those in there. Here's the sheet metal wall at knee level, the little wainscoting wall. So sheet metal, and then that's the normal XPS. And then we use these screws with these big washers on there to hold everything back. These are just tracks for the lights, and these are the fans, which I'll discuss later. But these are the backup fans that suck the air through the tubes when the solar chimney either isn't functioning as well as it should, or we have the doors open. That's the window that the flies come in and out of. It has you'll see when we get out there, it has a door that shuts, so we can shut both from the outside and the inside. It's automated. And this is pretty much the size of the room, and it's not that big, and you'll see that. We have lighting for the breeding facility, and this is one of the tubs for the soldier fly habitat. And we have everything on a little stand here because the plumbing goes under that to exit. So you can sort of get an idea. We have a narrow concrete floor. This is your access, and then your actual tanks are over here. Solar chimney is a framed angle iron frame with a sheet metal skin on the outside and a insulated inside wall and a glazing on the front. And the inside that whole thing is a sealed 14-foot, 10-inch duct pipe. That's basically what it looks like from the top. And drew it up for the guys to build. So it's 10-inch pipe, 2 inches of insulation. And that insulation is different than the other insulation. It's what they call polyisocyanurate, which is very heat-resistive insulation, still very highly insulative, but it's specially designed to take high heat because it will get hot in there, in that little chamber. And this is just the sheet metal painted outside jacket so that it's weather protected. And that's the front, which is it could be glass, but glass is expensive and it's also heavy. And this fiberglass reinforced plastic is a much better choice for this particular situation. This is right before we put it in. There's a hole in the roof we cut, facing due south. That's why it's crooked like that. The south is actually not flat with the building. It's actually cocked a little bit. So this is all sealed. That will get hoisted up like that, and then it gets bolted onto there. So there's a total communication between the inside of the room and the top of that thing. This is the terminus of the exit part of the pipe. They, of course, have to be insulated because in the ground they're working and they're gathering cool and heat depending on the season. But in the, when they get out, they don't have that protection. So we absolutely have to insulate them. This was labor intensive and time intensive, but it actually is fairly cheap and it works real well. These are just strips of the XPS cut into little wedges, long, skinny, wedge-shaped things that we can tape around the pipe. And then at the top, you'll see it's a little mushy up there. That's just spray-on foam, the kind you put in between your windows and your window frames, or the kind they put in new construction when they want to seal between the rafters and the plates or whatever they do in the attic, that kind of thing. So it's just a $5, $6 can of spray-on foam, and that just handles the corners, some of the corners, and the seal between the building and the tubes themselves. So that's what that looks like going initially, and then we have the close-up. Once they're taped on there, it's wrapped in fiberglass stripping, and this is basically a marine boat technology. This is what they use to cover wooden boats, to make fiberglass boats. You basically just lay layers and layers of this stuff over a substrate. So this is basically just a tape that gets dipped or soaked in this resin, and then you put gloves on and just wrap it around and wrap it around and wrap it around, and then there's a special paint. I don't have a picture of that paint except for the finished version, but there's a special paint which, of course, has to be white because we don't want to absorb heat. We want to reflect the heat. We're mainly looking at these as cooling tubes, so we want to get rid of as much heat as possible. So we paint the outside of them white so that it will reflect as much heat as possible. And you can actually go out and touch 95-degree day, and they are not, I wouldn't say they're cool, but they're not hot at all, really. They're nice and reflective. So it's telling me the inside of the tube, well, it's not just telling me, I know it is, the inside of the tubes are still very cool. Because the transition time, the residence time between the ground and that top of that building is very minimal. It's just a little short 12-foot or so. And so it's but it still can't just be left open to the sun, because the sun will bake those tubes and keep them too hot. Now at the inlet end, you don't really want to be sucking in hot air either. You want shaded air. So I'll walk up there and show you, but we just basically come out of the ground at a 45-degree angle, and then I put little angled outlets parallel to the ground because I really didn't want things falling down into the tubes. We definitely do not want any insects, squirrels, cats, or anything getting down in there, because you'll never get them out again. I mean, it's like, that would be awful. And then over the top, drape this, different names for it, but it has to be white, it has to be very reflective. So this stuff is used for cloches and greenhouse coverings and micro environments when you're starting seeds and stuff. So it's a lightweight, fairly tough. You just drape them over these hog wire type. You can see the inside of one there. Cloches, basically. Wooden stakes in the ground, hold those things into a hoop shape. This could just as well be a little shed. It could be a building. It could be a bunch of trees planted over there with overhang. We were thinking about doing that initially, but I just really wanted to do it this way, get something in the ground and get it done. So basically, it's just a good idea to protect the incoming air so there's some cool to start with, instead of, on a full hot summer day, it might be 97 degrees getting in there, if not more. We don't want to start that high. These charts are developed basically for well drillers and people who are building ground source heat pumps and things like that, but it gives you an idea of roughly, and this changes, site specifically, in a micro sense, will change significantly, or at least noticeably, from these numbers. But I'm just give you a rough idea. Say in Florida, it's pretty warm, 77 degrees, or whereas up in Maine, it's like, what does it say, 46? So we're talking about a pretty big swing. So what's that? That's Georgia, that's South Carolina. So we're here, 62 degrees, something like that. That's 30 feet. At 20 feet is not going to be a whole significant amount of difference. It's certainly not worth it digging from 20 down to 30 to try to get that extra degree of cool. There may not be a whole lot of reason, unless you can start from scratch in a situation where you have to sort of build up the soil. There may not be a whole lot of reason to go from, say, any more than 6 feet to make that effort to get to 10 or 12. If you have to dig for it, probably not. I mean, it's just, those machines are on a per hour basis are expensive, and you got help, and it can eat up your budget. So, from a safety standpoint, from an expense standpoint, 5-6 feet is very reasonable depth in our climate. Yeah.
We're talking here 30 feet versus 20 or 10 or 5. Is there some sort of research out there that might tell us more in this area what the Which area is?
The trouble is the research is not specific to this area. There has been research done at what different levels make what temperatures, and also correlations between how the seasons affect those temperatures and how the swing affects. In other words, if it's hot on August 15th, if it's 100 degrees out here, it's not going to be 100 degrees down there tomorrow. That takes weeks to get that heat down in. All that research is there, but unfortunately it's not here. There was research done in several Asian countries. There was research done in, I think it was Romania or the Ukraine. There's research done in Virginia. There was research done in Louisiana, I believe. And there's a lot of other places, but you have to really dig through. I mean, that's sort of your homework assignment. You can go through and dig through, and I've given you some links on the handout sheet. Good thing about those links is once you get to those links, you'll see notes at the bottom, and they'll give you some more links, and you can sort of look. This should be Virginia here. Pretty much what we're talking about, the ground temperatures on this side, and your day of the year from ground zero to the 365th day. See February, March, blah, blah, blah. You can get an idea of the depth. So here's the surface. There's 2 feet. There's 5 feet. There's 12 feet. And you can extrapolate between all that. And you can see that in this model, in the summer, say, or September, whatever the end of the summer, 69 degrees maybe at 5 feet. So we're at 6 feet. So you can sort of say it might be a little cooler. And lo and behold, the fineness of the soil affects the conductivity of the soil, how heat moves, enough that it's noticeable. Like sand is more of a coarse, so we're only moving at 0.44 BTUs per foot per hour. But say clay is a much finer substance, so you're getting 64. That's a significant difference. Loam is sort of in between. Once you start wetting the stuff, which the water really increases conductivity, look how much it goes up. And the reason the sand goes up so much is because sand is a coarse material. It absorbs a lot more water than clay will. Everybody knows that. Any gardener knows. Clay, you know how that is, it just runs off. But the sand is going to suck it in, so it's holding it. You got water and a substrate. It's there. It's going to really hold it. You dig a core sample. You want to actually dig a sample down 6 feet. You get a postal digger or something. You go and see what you got down in there before you start even thinking about doing any of this stuff. So this is an important part of the discussion. Now I said, we were 6 feet and changed a little bit from our 5 feet. Well, there's our temperature. And it's not, year round, but that's on a December 16th, the end of the summer, right before the end of the summer. Ambient temperature outside at the inlets where it's 90.5 degrees Fahrenheit. Temperature at the outlet in the building, in the exit of the tube, was 68 degrees. When you turn your air conditioner on, unless you really don't care how much money you spend on your energy bill, you don't really want to set the air conditioner much lower than that anyway. So, here we are. The other point is that these tubes also can help heat in the winter. We had to put that thermal radiant floor heating in. It had to be some type of heat. We could have just hauled in a little space heater. That thing is insulated enough that a little plug-in space heater would have taken care of our needs, but we don't do that at Living Web. We don't really want to do that. We want to do a resilient, responsible, and more of a natural and passive way of doing it. So we already had the heat available. It's a very low volume pump to pump the water through that floor, so that that's how we handled that. In the extreme depths of the winter, and especially if we get cold, we get a string of cold days, which is not that common here, but it happens. And in fact, it just happened this winter in our situation. The heat will have to be added there. The cooling and warming tubes aren't going to handle enough of that. That temperature is not going to be enough to warm that whole building, but at least it's going to be supplementing it. Depending on the type of day it is and whatever, the fan may have to be used to help pull some of that air through, because we may not have the solar draw on the worst of the winter days, especially if it's cloudy out and we don't have the heat coming into that solar chimney. There's the window. The outside door can be manually closed, and on the inside, I'll show you, we have a climate-controlled door that goes from the inside. This is part of our living roof class, which we'll have in September, I believe. There's 4 to 6 inches of earth up here, and just have some spring barley up here to sort of cover it. And we had planted some Chinese medicinal herb up here, which I don't think made it. That living roof helps temper the lags and the highs and lows of the temperature. Even though the inside of the thing is insulated, we also help with cooling actually by evaporation. If we, any water evaporating from that will help cool the roof of that container. Yeah?
Well, just know that the Jaguar is dormant right now.
Oh,
So
it
it
is?
may have made it, we'll see.
Yeah. The insulation is going to temper a lot of that, but it might drop it by up to 10 degrees. I mean, it might do that, maybe 5, But it wasn't the only reason we put it up there. It was really to have the living roof and to take the advantage. The other thing is we've never used these, but we've tested them. These are water curtain pipes. Basically, that's water from our supply that goes through tubes that are completely surrounding 3 sides of the building, so that if it really got hot and we just weren't cooling enough with the cool tubes and the earth roof and any way we could do it, those things shower the walls with water on a periodic basis, and that evaporation definitely pulls that heat out. So that's sort of a last ditch effort. It's on a temperature-controlled thermostat, which opens the valve when it needs to at whatever temperature we set it at. We could just go out there with hoses and do the same thing, but not if on a weekend when staff wasn't here and it was like 105 degrees outside, we weren't thinking about that. It could do some damage. The flies will go dormant if it's too cold, but there will be fatalities if it's too hot. And that too hot can range anywhere between the very high 80s Fahrenheit to about 103 or so. I mean, I have seen, just in researching it, I've seen significant survival in temperatures over 100, but that's not a risk we want to take. We want to keep our range in the mid 80s and something like that, and then start worrying about it past that. So, okay, let's go out back and just look at what we got outside.